In this video, I'll walk through a couple examples of linear programming for finite math. Now, for many finite math students, linear programming is new. You may have done a little bit of this at some point for another course or special project, but it could be that linear programming is really new to you. However, the different pieces that come together for linear programming are all a review from pre-calculus algebra, and also in our class it's a review of some of the things we did in Unit 1. So let's break this down into some nice easy chunks that are easy to do. Notice that for the problems we're going to work, the first example says to set up the system and graph it, but you don't need to solve it. And then for number 2, we'll actually solve it. What I've done is I have read the problem and I've organized the information into a chart. And here's the chart. I'm going to leave that part for you, so go ahead and read that problem and maybe even pause the video and confirm that you understand where each of the pieces in the chart come from. I don't want to make this video too long, so I'm going to leave that part out for now, but I'll tell you that each of the pieces in the chart just come directly from the reading of the problem. And so follow that along and I'll talk through the different constraints as we go. But once I've organized the information, what I see is, and hopefully you've paused the video and read that problem, because otherwise the whole example is just going to make no sense to you. But what we do is we've got a special sandwich and a basic sandwich. The special sandwich has vegetables and cheese. The basic sandwich has vegetables and cheese, but different amounts. So what we can do is we could let X, as we need to define our restraints, we let X equal the quantity of special sandwiches and let Y equal the quantity of basic sandwiches. We want to actually write that on the page somewhere so we remember what our variables are representing. And then if I want to write an equation for each of these, for the vegetables, how much the vegetables are going to cost. The vegetables are going to cost $2 times however many special sandwiches we have, plus $1 times the number or quantity of basic sandwiches. And for vegetables, we've got to keep that at or below $32. Next, we could write an equation for cheese, or I'm sorry, not an equation, but rather an inequality, right? So the cost for the cheese, we have to keep it less than or at $100. And the cost for cheese is $5 times the number of special sandwiches plus $4 times the number of basic sandwiches. And that's going to come out to a total that's less or equal to $100. Here's our constraints. That's the first step to this problem, is listing the constraints, right? And then we could also write the other constraints that we're given, that X has to be greater, the number of special sandwiches is always going to be greater than or equal to 6, and the number of basic sandwiches, Y, is going to be greater than or equal to 4. Next, I'm going to graph these, but I know that for graphing these, especially when I graph the green and the orange, it's going to be important to know where they intersect. And it's also going to be helpful to have these solved for Y, so that I have it in y equals mx plus b form, right? So that I can easily graph it. So if I were to solve the vegetable inequality for y, that's really easy. I'll just subtract 2x from both sides. So y is less than or equal to negative 2x plus 32. For the cheese, a little bit more challenging, not that much, but let me change the color so that we match up. We'd have, if I subtract the 5x from both sides, 4y is less than or equal to negative 5x. So subtract 5x from both sides, plus 100. And then when I divide by 4, what I get is that y is less than or equal to negative 5/4, so negative 1.25. Negative 5/4. Don't write it as a decimal though. Write it as a fraction, because when I go to graph this, that's going to be a little bit easier to work with, plus 25. Now it's going to be really important to get where these two intersect. So I'm going to solve this system to see where they intersect. And I'm going to go ahead and do that before I graph, just so I can keep on track with my graph. Really easily, I could use a substitution method since they're both solved for y. So I could set the two equal to each other. If they're both equal to y, the negative 2x plus 32 is going to be equal to negative 5/4 plus, oh, I left the x off of there, didn't I? Negative 5/4 x plus 25. You could use a calculator to do some of this arithmetic, or you know what I'm going to do? I really don't like keeping the fractions in there, so I'm just going to multiply everything through by 4 and then solve for x. So we have negative 8x plus 128 equals negative 5x plus 100. I could add 8x to both sides and subtract 100 from both sides. So I get 28 is equal to 3x. So it looks like they're intersecting at x equals 28/3. And I could then plug that into either equation to find y. So if x is 28/3, y is negative 2 times 28/3 plus 32. I could take any of these four inequalities and write their equivalent equation and then get this. I just took this first one, y equals negative 2 times x, so x is 28/3 plus 32. So it looks like those two lines, the cheese and vegetables, intersect at x equals 9 1/3, y equals 13 1/3. I can write that as a 1/3 is 3 with a repeat. The 3 keeps repeating, so I could write that with the bar over it. Let's go ahead and graph those two lines. And I do like using the colored pencils to do the graphing, because those colored pencils really help me to see keep separate the two equations or an inequality. So I'll start with the line y equals negative 2x plus 32. We'd start just above 32 and go down 2 increments, 1, 2, and write 1 increment. So we can see those points that are plotted, and I could draw that line. Now, notice that I've only, in my axis, my XY axis, I've only included quadrant 1, where x is positive and y is positive, because we're not going to be concerned with quadrant 2, 3, and 4, where x's or y's are negative. And then I could shade everything below that line, because the inequality is less than. So that's this green portion here. Now I could do the same for the cheese function. And by shading with some color, I can see that the part that they both share is a part that's both green and orange. I'm going to go ahead and plot in my corner point, because I already found that the 9 1/3, 13 1/3, I found that corner point, so I know exactly where they're intersecting already. And now we have two more constraints to graph. We have x greater than or equal to 6. So here's the line. Oh, I graphed that. I started to graph that as y equals 6, right? But the x equals 6. When x is 6, we get that vertical line. And then we've got our y equals 4, just below the 5 mark. So our y equals 4. We could pull out and name those other quadrants. Oh, you know, let's go ahead and shade in, just to be really clear here. The greater than 4, that's all of this, right? The only part I'm really going to be concerned with is the part that's in that region, because we're looking for the pieces that are inside our polygon. If we do the shading for x greater than 6, it's all of this, right? But again, all I'm going to really be concerned with is this part inside. Can you see through all of that where we've got the intersection? I'm going to back up and unshade that pink and blue, just so we can see this a little better. But the region that we're going to have is this polygon here. It's not really a triangle. I've gone through and outlined that polygon in black. Well, we've got one of our intersection points. We need to find the others, find and name those. Because what we know from linear programming, what we know is that if there is a minimum or maximum, because we want to minimize our costs, right? To find that minimum or maximum, what we want to do, what we know is that it's going to happen at one of those 4 corner points. So the corners, we already found the hard one. That's the 9 1/3, 13 1/3. Here's an easy corner. We've got x equals 6, y equals 4. Another easier one, when x equals, what was this? When we get the green intersecting with the blue, if we want to find the intersection of the green and blue, then we could say that when y equals negative 2x plus 32 and y equals 4, that gives us 4 equal to negative 2x plus 32. Solving for x, we get x equals 14. And when x equals 14, y equals 4. Well, y is always 4, right? So we could write that corner. X equals 14 and y equals 4. And when the orange and red intersect, 5x plus 4y equals 100. And when x equals 6, that gives us 5 times 6 plus 4y equals 100. So 30 plus 4y equals 100. Subtracting 30 from both sides, 4y equals 70. So y equals 70 divided by 4, or 17 and a half. 70 over 4, so that's 35 over 2, which is 17.5. And what does x equal? X equals 6. So we'd have 6, comma, 17.5. So it looks like we have our corners. We're all set up. We have named our corners. And if we had an objective function, which we don't for this one, if we had an objective function, we could use that function to see which of these 4 corners minimizes cost or maximizes profit, whichever it was, whichever that objective function was doing. But this is sufficient for this problem. I know it's pretty involved, isn't it? But you can do these. It does take a little bit of practice. Let's jump to the next one. In this next example, once again, I have written out a chart, and I'm going to write the equations that I can use for each of those charts. Pulling the information out of the problem, I can write these constraints. So I've organized the information in this chart, the calories, the vitamin A, the vitamin C, the total number of calories, vitamin A and vitamin C that are needed. So I could write the constraint for calories, 60 times the number of TrimFit servings, plus 50 times the number of U-Save servings, has to be greater than or equal to 300, because that's the calories. 60 calories for every serving of TrimFit, 50 calories for every serving of U-Save. And by the way, how did I determine which was the X and Y? Well, in this number, or letter C, they tell us just to keep everyone's work consistent, we could do these opposite and it would work out to the same answers. It's just that to keep everyone's consistent so it matches up. In this video, we're going to let TrimFit, we're going to define X as the quantity of servings of TrimFit. Let X equal the number of servings of TrimFit, and then we're going to use the vertical axis. So the vertical axis, that's the y-axis, is the U-Save servings. So the 60 times the number of TrimFit servings plus 50 times the number of U-Save servings is greater than or equal to the total of 300 calories. 8 for the vitamin A, 8 times X plus 20 times Y is greater than or equal to 80, because we have to have at least 80 units of vitamin A. And then 6 for vitamin C, 6 times the number of TrimFit servings plus 30 times the number of U-Save servings, so 6x plus 30y is greater than or equal to 90. Notice how I've color-coded each of those so that when I graph the lines, they match up on the graph, and I don't have to think really hard about which graph goes where. And then the objective function. If TrimFit costs 25 cents a cup and U-Save costs 32 cents to make, not to buy, per cup, then we could say that the cost is 25 times the number of TrimFit, so 25x, plus 32 times the number of U-Save servings. So the objective function, C equals 25x plus 32y. So list the constraints, that's here. Part A. Part B, determine the objective function. Part C, next we will graph. After we have our constraints and our objective function, if we're going to graph these constraints, we're going to do that most easily by solving for y, so that we get our y equals mx plus b, where b is the y-intercept and m is the slope. So if I subtract 60x from both sides and then divide by 50, I get y is greater than or equal to negative 6/5 x plus 6. Subtract 8x for the vitamin A, the pink. Subtract 8x from both sides and divide by 20. I get y is greater than or equal to negative 2/5 x plus 4. And then for the vitamin C, the green, if I subtract 6x from both sides and divide by 30, y is greater than or equal to negative 1/5 x plus 3. And with precision, with a great deal of care, I'm going to graph these. And here's why I say with precision. I could save myself the trouble of solving these intersections algebraically by graphing them precisely. And on this one, it just happened that those intersections came right on corners in the graph. So by using some graph paper to graph and by really counting out carefully, I found those corners without even doing the algebraic solution of the system. You can still go back to do the algebra to check those, but let's see what happens when we graph. If I graph the calories as blue. And if I graph the related equation, y equals negative 6/5 x plus 6. Start with 6 and then drop down 6 and write 5. Or if I drop down half of 6 to 3 and write 2.5. I'm going to mark that in here that this is 2.5, right? And then for the vitamin A function, starting at y-intercept of 4, drop down 2 and write 5, down 2 and write 5, and I've done that in pink. And then the green vitamin C, starting at the intercept of 3, and then I drop down 1 and write 5. See, I land right on that point where the pink had already been, right? Then down 1 and write 5. Down 1 again and write 5 brings me all the way out to 15. So you can see that all of those corner points are nameable right off of the graph, but you could go back and do some algebra to find those. So we've done the vertices of the feasible region, and the feasible region goes infinitely out, right? If we wanted, I don't want to graph it on here because I don't want to make the graph unclear. I take that back. I'll go ahead and graph it so you can see it, because I realized I could graph it with a really light highlight. But you see the feasible region, because all of these were greater than. So this part that goes out, the part of the graph that goes out, so up. In that feasible region, we know that the minimum for the cost is going to occur at one of the 4 corners. So rather than test an infinite number of ordered pairs, we know that this cost will be minimized at one of these 4 points. So all I have to do now is find each of those costs. So I'll substitute a 0 in for x and 6 in for y. You know, this wouldn't be a bad place to pause the video and do this algebra yourself just to see if we're getting the same results. But I'm going to substitute a 5/2 in for x, a 3 in for y, 5 for x, 2 for y, 15 for x, 0 for y, and get each cost. When I do that calculation, that arithmetic, I'm getting the cost minimized when x is 5/2 and y is 3. So in other words, 2.5 servings of Trim Fit with 3 servings of You Save would cost $158.50. So it looks like that's our minimum. I'm going to write that out for part E. How many cups of each drink should a person consume? Therefore, consume 2.5 cups of Trim Fit and 3 cups of You Save to minimize your cost. And what is the minimum cost? So part F, we'll write it on that line on your worksheet. The minimum cost of 2.5 cups of Trim Fit, 3 cups of You Save is $158.50. Wow, that was quite a problem. These are not quick, easy examples, but they're so doable. You can do this. I know it might be new to you, but work through the examples and do each one carefully. And if you do need further help with this, try watching the video again. Try doing these 2 problems without the video, so try doing them on your own. And then if you do still need some further explanation on any part of these problems, please reach out to me. I know I skipped a little bit of that algebra for the sake of time, but feel free to reach out to me if you need a little bit more guidance. And thanks so much for the work you're doing. And that concludes this video.